Alright, so in this video I'm going to be explaining another important paper with the title Graph Positional Encoding via Random Feature Propagation. This positional encoding is a real challenge in graph neural networks, in transformers, in graph transformers, even in generative models like diffusion, because it is on top of these things like GNN and transformers, you still suffer from this. And there are naive approaches and very systematic approaches to handle that. So this ICML paper in 2023 is very interesting. Two main families of node feature augmentation scheme have been explored for enhancing graph neural networks: random features and spectral positional encoding. Surprisingly, however, there is still no clear understanding of the relation between these two augmentation schemes. Here, we propose a novel family of positional encoding schemes which draws a link between the above two approaches and improves over both. The new approach, named random feature propagation, is inspired by the power iteration method and its generalization. It concatenates several intermediate steps of an iterative algorithm for computing the dominant eigenvectors of a propagation matrix, starting from random node features. So this is an overview of our random feature propagation. We start with the k-dimensional random node features and perform a series of propagation and normalization steps according to predefined or learned propagation operator. We then use the whole trajectory as a node positional encoding. As a result, the network has access to features ranging from pure random features to features that approximate the dominant k eigenvectors of propagation operators. So there are four main components. The first component is a type of RNF used by our method. Two distributions are considered: standard normal and Rademacher's distribution. Other distribution may also be suitable. The second component is the propagation operator, which governs the information flow between nodes. The third component is the normalization function, which returns a normalized representation of the current node features. So in order to compute our positional encoding, we sampled the random features from some joint probability distribution and perform P of the following iterations. And S is the propagation operator, N is the normalization function, and this omega is a positive integer hyperparameter that controls the frequency of normalization step. So we define a feature trajectory as the concatenation of initial random feature R and P steps defined in equation 1. So we are concatenating all of these. In order to reach our positional encoding, it may be helpful to use several trajectory inputs that originate from different random samples. So we concatenate and embed our positional encoding and input node features using a linear layer followed by an optional nonlinear activation. So we consider two popular predefined operators: the symmetrically normalized adjacency matrix with added self-loops and the analogous symmetrically normalized Laplacian matrix. So we additionally propose to learn propagation operator. The advantages of using learnable operators are twofold. First, propagation by fixed operator may not produce suitable features for learning tasks. Second, our learnable operator can capture pairwise node interactions that are difficult to model using the previously proposed local operators. This is the workflow when using a learnable propagation operator. So we start from the original node features, process them with GNN, apply attention. Then we use the operator, the resulting operator, to generate our positional encoding. A second key component of our RFP framework is normalization framework. Because from practical standpoint, a normalization steps helps to control the magnitude of the features, which may grow exponentially with the number of iterations depending on the propagation operator S. So the first normalization we consider is just a simple channel-wise L2 feature normalization. This normalization is applied independently to a channel of the propagated node features. The second normalization method is the joint channel-wide orthonormalization of node features. So we propose to couple our RFP positional encoding with two kinds of architecture. The first is just a standard message passing neural network or transformer that consumes the initial embedding. So this is a single layer of the proposed DSS-GNN architecture for processing multiple trajectories. So given multiple trajectories, we first apply an embedding function to each trajectory independently, then reshape these embeddings. So I've explained this paper, this idea in a different video. But the idea is these layers that we define like this. And this is the data set they use, Zinc 12K and OGB Olive HIV data sets. But the backbone is GINE for all baselines. And you see the node classification accuracy for example, Chameleon and Squirrel, they are not homophilous, they are heterophilic. That's why it's very difficult. The rest of them are very easy. It's a very interesting paper.